Hey everyone, and welcome to today's Explainer. I am absolutely pumped to have you here. A lot of people look at a page of math homework, especially CBSE Class 8 math, and they just see this intimidating wall of tedious numbers and equations. But we're going to completely flip that perspective today. We aren't just sitting here doing boring homework. We're going to act as mathematical detectives. Our mission? Uncovering the hidden, invisible identities, secretly pulling the strings behind these equations. So, grab your magnifying glass, because things are about to get really interesting.
I want you to ask yourself honestly, can you uncover the hidden identities inside mathematical equations? When you're looking at a chapter like rational numbers, specifically exercise 1.1, these questions aren't actually asking you to just crunch numbers for a random answer. Nope, they're asking you to spot a secret rule. Solving these problems isn't about rote memorization. It's really just a fun, highly logical game of pattern recognition. And once you learn how to spot the patterns, well, you win the game.
To completely crush this exercise, we need a solid method. So here's our 3-step detective toolkit for today's investigation. Step 1, look very closely at the exact question, the raw numbers themselves. Step 2, abstract those numbers to analyze the underlying formula they form. Step 3, once that formula is exposed, we simply name the hidden property. If we stick to this toolkit, there is literally not a single equation in this textbook that can trick us. All right, let's jump straight into Section 1, Puzzles of Rational Numbers and the Magic Power of 1. Okay, let's dive into this. Here is the exact numerical equation we're presented with. -4/5 times 1 is equal to 1 times -4/5, which simply leaves us with -4/5. Now, I want you to focus intently on that number 1 sitting right there in the middle. What is it actually doing to our rational number -4/5? Is it changing the value? Is it shifting the sign? Are you seeing a pattern here? On the left, we've got our raw numerical equation. But look over to the right. If we strip away the specific numbers and replace them with abstract variables, we get a over b times 1 equals a over b. By pulling away the specific numbers, the core mechanism is totally exposed. Any rational number multiplied by 1 just gives you that exact same rational number right back. Its core value? It never, ever changes. And boom, there's our satisfying aha moment. We can officially close our very first case by naming this property. This is the multiplicative identity, or commonly known as the role of 1. It's basically a mathematical guarantee that multiplying any rational number by 1 will always, without fail, return that exact same rational number to you, completely unharmed and unchanged. Moving right along to Section 2, the rule of changing places. Let's check out our next clue and see how this builds. What property is being used right here? -13/17 times -2/7 is equal to -2/7 times -13/17. Now hold up, don't actually do the multiplication here. Instead, put your detective hat on. Pay close attention to what happens on the left side of the equal sign compared to the right side. Now, what's really fascinating is how obvious the pattern gets when we abstract it again into our toolkit's formula view. On the left side, we have a over b times c over d. On the right side, it is completely swapped to c over d times a over b. It's a clean, perfect position swap of the fractions. They literally just traded places across the equal sign. So we can confidently name this the commutative property. The commutative property tells us that changing the order, or, commuting the positions of the rational numbers during multiplication doesn't change the final product at all. Just like 2 times 3 is the exact same as 3 times 2. In this specific scenario, the order simply does not matter. Mystery number 2 officially solved. Let's keep the momentum going. Section 3, the game of multiplicative inverse. Take a real close look at this equation. -1 over 29 times 29 over -1 equals 1. Do you see the physical trick happening here? The -1 from the top is now on the bottom. The 29 from the bottom is suddenly on the top. They completely switch their numerator and denominator positions, and magically, this whole chaotic mess just collapses into the number 1. Let's pull out our toolkit and abstract this. We start with an original fraction. Let's call it a over b. We multiply it by its exact opposite, or its inverted fraction, which is b over a. The a on top cancels the a on bottom. The b on the bottom cancels the b on the top. Any fraction multiplied by its exact inverted version creates this super neat, perfect cancellation. We can close this specific mystery by declaring that this beautiful, neat cancellation is called the multiplicative inverse. Multiplying a rational number by its exact inverted counterpart will always result in 1. It's like mathematical balance at its absolute finest. So if you ever see a fraction multiplying by its upside-down twin to equal 1, you instantly know you're looking at the multiplicative inverse property.
All right, leveling up. Section 4, the property of shifting brackets.
Look at this equation. 1/3 times open bracket 6 times 4/3 close bracket equals open bracket 1/3 times 6 close bracket times 4/3. Quick side note, that whole number 6 can easily be imagined as the rational number 6 over 1, just so our brains keep it cleanly in the rational format. But really, I want you to spot the movement of the brackets here. And this brilliantly illustrates our underlying formula. Just look at the abstraction. On the left-hand side, our brackets are grouped around the back two numbers. But on the right-hand side, the exact same numbers are sitting there in the exact same order. But the brackets have shifted to group the front two numbers instead. The grouping shifted, sure, but the equal sign tells us the final value remains absolutely identical.
We call this shifting of groups the associative property. It clearly states that the grouping of rational numbers, meaning exactly where you decide to place those brackets, does not affect the final multiplication result. As long as the operation is all multiplication, you can associate the first two numbers together, or the last two together, and the equation simply won't break. That is the defining trait of the associative property.
Almost there, detectives. Section 5, the final rule of multiplication. So, here is the question posed to us. The product of two rational numbers is always a blank. I actually want to pose this question directly to you right now. Before we prove it mathematically, what do you think goes in that blank? If I multiply a fraction by a fraction, what foundational category of number do I actually get back?
Well, the crucial point is right here. Let's test this out by looking at a quick table. We take rational number 1, 2/3. We multiply it by rational number 2, 4/5. We multiply the numerators, 2 times 4 is 8. We multiply the denominators, 3 times 5 is 15, giving us a final product of 8/15.
Now, let's quickly remind ourselves of the core absolute definition of a rational number. It has to be able to be written in the form of p over q, where p and q are integers, and most importantly, the denominator q cannot be 0. Well, look at our product. 8/15 is exactly in the form of p over q, and our denominator is 15, which is for sure not 0. It fits the rule perfectly. So we can officially fill in that final blank. The product of two rational numbers is always another rational number. We call this foundational rule of multiplication the closure property. It basically means that the set of rational numbers is closed under multiplication. If you stay inside the world of rational numbers and multiply them together, you will never, ever escape that world. Your answer is always going to be a rational number. And there you have it. We did it. We solved literally every puzzle exercise 1.1 threw at us. But I want to leave you with this final thought. If math is truly just a series of hidden patterns waiting to be named, what other invisible rules are operating in the equations you solve every single day? Next time you sit down with your homework, don't just mindlessly calculate. Look for the patterns. Look for the invisible rules. Become the detective. Thank you so much for exploring these mysteries with me, and hey, keep hunting for those patterns.